Well, greetings, friends, and welcome to Math 222. This is Calculus 2, which means that I assume that all of Calculus 1 you have seen and are competent with. And so we hit the ground running at the beginning of Calculus 2. We begin with a few weeks looking at transcendental functions. Well, what the heck is a transcendental function? Well, it's pretty much any function that isn't algebraic, any function that cannot be expressed as a polynomial. And so if you're familiar with AP Calculus AB, we're going to take some time looking at exponential functions and logarithmic functions for a few weeks, their properties, their derivatives, things of that nature. So we kick off by taking a look at what we mean by one-to-one functions. So what the heck do we mean by one-to-one functions? Well, we say that a function f of x is 1-to-1 on some domain D if f of x1 is not equal to f of x2 whenever x1 is different than x2 in D. Now, luckily, you're watching a YouTube video, so you can hit pause if you're thinking, what in the world is that? But really, this is an idea that you're familiar with. If you've taken any sort of pre-calculus course, you've probably taken a look at functions like this, and you've said that these are one-to-one functions, because if I pick an x1 and an x2 that are different, f of x1 and f of x2 are different. Whenever x1 is different than x2, f of x1 is different than f of x2. And so you've, of course, played this game where you have some function like so, and you say that that function is not one-to-one because it fails the horizontal line test. Well, what does the horizontal line test do? Well, it says if I draw a horizontal line like so, and that horizontal line hits the function in more than one place, then my function cannot be one-to-one. Well, why does that work? Well, that works because in this scenario, here's an x1 and here's an x2. They are different. x1 is different than x2, but f of x1 is equal to f of x2. And so we have a scenario where x1 is not x2, but their outputs are equal. And so this green function is not one-to-one. Well, let's play everybody's favorite game. This will be our first OYO. This will be an on your own. That's texting language for on your own. Are they one-to-one? It's a great theme song. Are they one-to-one? Hit the pause button, draw 4 quick graphs, and convince yourself that they are or are not one-to-one. Ready, go. No, really, hit the pause button. Really, hit the pause button. See, you waited too long. You waited too long. There are your 4 answers. The no's could be yeses if we restrict the domain. If we restrict the domains on our 2 no's, we can get functions that on a particular domain are one-to-one. When we talk about a function being one-to-one, we usually refer to its entire domain. And so in these scenarios, the functions are not one-to-one, not on their full domains. So let's talk about the other thing you're probably familiar with from some high school pre-calculus course. Let's take a look at what we mean by inverses. So we're going to suppose that f is one-to-one on some domain D with some range R. Notice the use of variables. The inverse function, and we're going to denote the inverse function with a capital F to the, with a lowercase f to the -1 power. Now that's different than the -1 you learned in Algebra 2. In Algebra 2, you learned that when you see a -1, that just means you do 1 over the thing. This will not fly in this course. In fact, I should make that a different color. This will not fly in this course. The inverse function, f inverse is how that's read, f inverse, is defined by f inverse of b is a if f of a is b. So if f of a is b, then f inverse of b is a. Really, all we do is flip-flop where the x's and y's are. We flip-flop the inputs and the outputs. So what does that mean? Well, that means that the domain of f inverse is the range of f, and the range of the inverse is the domain of f. And this happens simply because we are flip-flopping inputs and outputs by definition. So let's flesh this out. Let's pretend, we'll blow up the little red trolley and pretend that I have some function and it goes through -2, 0, and it goes through 0, 2, and it goes through 4, 4, and it looks roughly like this. This is some function f. And we'll pretend that I'm interested in graphing f inverse. Well, how do you graph f inverse? Well, -2, 0 flip-flops to 0, -2, and 0, 2 flip-flops to 2, 0, and 4, 4 kind of flip-flops to 4, 4, and you get some graph that looks like this. All the x's and y's flip-flop. You will notice, because you're bright, that if you were to throw y equals x into the picture, that y equals x is the mirror between f and f inverse. So we note here, this is our first side note of the semester. Here's a side note, la, f inverse is the image of f after a reflection in y equals x. So all of you folks who love transformational geometry are going to love that. From an algebraic standpoint, we could find f inverse of x. Yes, that's f inverse of x. Boy, is that awful. Way to go. Nice job. If f of x is -2x plus 4. We will note that this function will pass the horizontal line test. That's not too terribly difficult to see. This function is y equals -2x plus 4. In the inverse case, the x and the y flip-flop, and this is something that you probably remember from your Algebra 2. You trade x and y, and then your job is to solve for y. I want y all by itself like I was as a kid for so long, and so we just solve for y. And so what's our answer? The inverse function is this thing. Mr. Reuter, do I have to write this as -1/2 x plus 2? Well, you could, falsetto boy, but you don't have to. You can leave it in this form unless you're asked for things in the form mx plus b. Nothing that says you can't leave it like this. How do you check yourself? How do you check yourself? Do a discount double check. To do that, we would compose f with f inverse, or f inverse with f. And if we were to do that in either order or both orders, we should get x as the result. And I'll leave that to you in the privacy of your own home. So you're in Calc 2, and let's go back a few slides. This is not calculus, this is not calculus, this is not calculus, this is not calculus, this is not calculus. No derivatives in sight. So the question is, where is calculus? And the answer is right here. This is exploration 1, which is cut off at the top, which is just awful. But it should, in theory, say calculus 2 with Rooter, exploration 1. And now it does. Yay! Oh, wait, no, it doesn't. Yay! Okay, so what I'd like you to do for a little while is hit the pause button and play with this. This file is up in my courses, so you can actually play with this for a few minutes. I want you to graph a quintic. I want you to answer some questions about it. I want you to find its derivative, and that should help us to conclude that f will indeed have an inverse. I want you to reflect the graph over y equals x to get a graph of the inverse. You won't do that on your machine. You'll do that by hand on a sketch, and then you're going to sketch a tangent line. Because see, what I'd like to do is I'd like to find the slope of a tangent line to an inverse function, but I'd like to do that without finding an equation for the inverse function. Sure, the inverse function has an equation, but I'd like to do this without that step if I can, because that will make my life just a scotch easier. And then when that's all done, I'd like you to actually do the reflection. I'd like you to reflect the line over y equals x, find the slope of the reflection so that you can find the slope of our line in question, and then find the derivative of the inverse function at x equals 2. Now, sure, you can just wait 10 seconds after I stop talking, and then I'll give you the punchline because that's part of the video, but I don't know that you want to do that. I think you want to figure this thing out because you can figure this out. So take some time, hit the pause button, get that done, and I'll see you in a few seconds. Did you really do it? Did you? I can't hear you. I'm not Dora the Explorer. I can't actually hear what you're doing. So the theorem that's in play goes something like this. If I want to know what the derivative of an inverse function is with respect to x at some point, let's say that it's b, and I happen to know what the derivative of the original function is with respect to x at wherever the inverse of b is, then those two quantities are reciprocals. And that almost makes sense because, again, we trade the x's and the y's. The x's and the y's trade places. And when you do that for slope, dy dx becomes dx dy, you would expect a reciprocal relationship in that spot. You expect those to be reciprocals. So let's find the derivative of the inverse of y equals 2x cubed plus 12 at x equals 14 without finding the equation of the inverse function. We could, in this scenario, find the equation of the inverse function. We could swap out x and y, subtract 12, divide by 2, take a cube root, and then take a derivative of that using the chain rule. But let's pretend that we stink at the chain rule, and we'd like to do it a different way. There is some point on the inverse function with an x-coordinate of 14, which means that there is some point on the original function with a y-coordinate of 14. 14, 1? 1? Are we okay with that? 114 is on the original function, which means 14.1 is on the inverse function. Now that's a key, because I'm looking for the slope of the tangent line there. But I'm going to find the slope of the tangent line there and use that to get the answer that I want. Some of them want to use u, some of them want to be used by you. Sweet dreams are made of these. Who am I to disagree? Derivative of this thing, 6x squared? 6x squared. Great. I want to evaluate that when x is 1. This one. That turns out to be 6. So the slope of the tangent line here is 6. So the slope of the tangent line on the inverse here is the reciprocal of 6. The inverse function has a derivative at 14 of 1/6. And you are all set now. You now know how to find derivatives of inverse functions without finding equations of inverse functions, which is somewhat more powerful than you thought it was. All right, you've stuck with me for almost 20 minutes, and I'm so glad that you did. Next time, who knows what's up next time? Well, you do if you've seen the playlist. All right, thanks everybody.